Hello everyone, and welcome back. Today we're going to talk about internal energy, and along the way I thought this would be a really good opportunity to introduce bar graphs. So when I first introduced the different types of energy we'll be dealing with, I introduced internal energy like this: energy transfer due to friction. Now, even though the term thermal energy is probably a little more appropriate for this, the College Board decided to use this term because you were going to use it in a very specific manner in the first year physics course. So I have it defined as energy transfer due to friction. So if you were to rub your hands together on a cold day, your hands would warm up. That, in a nutshell, is internal energy. Now, along the way, I want to introduce something that's even more important: energy bar graphs. So what I have on the screen right now is a blank energy bar graph. The reason why it is good to use one of these is because since energy is conserved and can neither be created nor destroyed, it is a good idea to have a way to keep track of it. And an energy bar graph is a really simple way to keep track of all the energy and what types of energy you have. So let me show you a few examples of how this works. Let's say we have a situation: an apple falls from a tree. At what velocity will it hit the ground? Our system is the apple and the earth, and there's an assumption here that the original velocity of the apple is zero because it was hanging in the tree. Well, in our initial state, we have gravitational potential energy. I'll draw a bar here. When the apple touches the ground, all of the gravitational potential energy is transferred into kinetic energy as our final state. We would then use this transfer to make a relationship between the initial state and the final state.
From this point, you can solve for any single missing variable in this equation.
So now let's take a look at a similar situation. An apple falls from a tree. What velocity will it have when it has fallen 3/4 of the way to the ground? Same system, the apple and the earth. Well, our initial state is still the apple hanging in the tree, so we have gravitational potential energy. Now, if it's 3/4 of the way to the ground, I'm going to roughly split this into 4 pieces. That means since the apple has not touched the ground yet, there is still some potential energy left. And since potential energy is mg delta y, it means 1/4 of the distance is left, therefore 1/4 of the potential energy. So that means 3/4 of the energy is still as kinetic. So using that, I can set up a relationship with the initial and final again. As a side, I'm using h and y interchangeably because some classrooms like to use one and some like to use the other. I will accept either. Now, how about this situation? A box starts at rest on a frictionless surface. A man pushes the box to the right, increasing its velocity. The only thing in the system is the box. Well, in my initial state, I do not have kinetic energy because there's no velocity. I have no gravitational energy because there's no height, and there's nothing elastic in this problem. In my final state, the box will have kinetic energy because it has gained velocity. Now, if I have no initial, but I do have final energy, that means energy entered my system, which means that work had to be done. The energy came from the person, and the person is not in the system. So that means I have force parallel delta D equals 1/2 mvf squared. And since there's no friction, this force parallel is going to be force person on box. So if I was given the displacement, mass, and final velocity of the crate, I could find how much force was used, or if I was given the force, displacement, mass, I could find the final velocity here. Now notice I said frictionless. Let's bring up one more problem. A box starts from rest on a surface with friction. A man pushes the box to the right, increasing its velocity. Now we have friction involved, which means if I did a quick force diagram, I have force person on box to the right and force friction to the left. And both of these are now parallel to the displacement, so both of them would be work if the box was the only thing in my system. And that's what I want to talk about today. Because notice in each of these problems, I purposely mention the system. And in energy, that is extremely important part of the problem. Okay, to do this, we're going to take a look at two very similar problems. I have a book. It is currently sliding to the right at 2 meters per second. The book slides to a stop due to a frictional force. I have the mass of the book and the distance it travels before it comes to a stop. I have the system first as just the book. Here I have my bar graph. In the second situation, everything is exactly the same except for one difference. In this case, in my system is also the table that the book is touching. In both cases, the force diagrams would be identical. Force earth, force table and book, which is force normal, and the frictional force, which slows the book down to a stop. Now, here is the order I recommend you create your bar graph in. First, do the initial state. In my initial state, it has a velocity to the right, so there is kinetic energy. There is no height, so no gravitational, nothing elastic, so no elastic potential energy. The second thing you want to do is take a look at our final state. Since the book has come to rest, there's no height, nothing elastic, and we'll deal with internal energy later, there's nothing here. So there's no energy in the system in our final state. Therefore, if we have initial kinetic energy, but no energy in the final state, that means work had to be done, which is the third thing we check. And since we have energy and energy need to be removed, that means the work needed to be negative. So I will draw it down here. And internal, we're going to discuss in a minute, which means energy was removed from the system. Well, what removed the energy from the system? The table did, because the table provided the frictional force. Now, if the table is not in my system, it cannot be one of my energies, which means the table did work on the system. And since the displacement was to the right and the force was to the left, that means I have negative work. In other words, displacement is positive and force is negative. And looking at my equation down here, I get a negative work, which means energy is removed from my system. So then creating this relationship, I'll start out with the kinetic energy formula. Now, notice I drew the bar underneath. That means the energy was removed from the system. In other words, it is negative work. And what force is the force parallel? Well, that is force friction times the displacement equals 0. So if I'm given mass, VI, and displacement, I can find the frictional force here. Now let's take a look at the exact same question with one difference. If I keep the table in the system, again, I'll start with my initial, kinetic energy. Now, the second part I want to look at is the final. The book had kinetic energy. Energy can't be destroyed, so where did it go? Well, as the book slides across the table, energy is dissipated into the table as internal energy. And if the table is part of my system, I can actually keep that energy in my bar graph. So in other words, if I took the book and slid it back and forth for a while, the table would become warmer. That's evidence that the energy is being transferred into the table itself. And since this accounts for all my energy, I don't have to worry about work. Since the table's in my system and the energy went into the table, the energy did not leave my system. Now, since in a first-year physics course, you will only be dealing with internal energy as a transfer from friction, the force from this is always going to be from force friction. So it's force friction times displacement.
Something to keep in mind here is that this does not reference the force friction on the book. It references the force friction on the table. In other words, if the table is exerting a frictional force on the book to the left, then the book is exerting a frictional force on the table to the right, which is the positive direction.
Now notice this equation and this equation essentially say the same thing. I'm also keeping track of all the energy I'm dealing with. It also opens up other possible sources of work. Let me show you what I'm talking about. All right, this time we're going to take a look at a very similar situation. The only difference is there's going to be a force from someone's hand pushing the book to the right. The book is still going 2 meters a second. It's still coming to a stop. Mass is still 1 kilogram. Displacement is the same. Force hand of book is 4 newtons. And let's say we're looking for force friction. Again, here are the rest of the forces on the book. Now, first, again, the system is just the book. One, I'll look at my initial state. The book is moving. Therefore, I have initial kinetic energy. Final state, the book comes to a stop. In other words, the person isn't pushing with enough force to speed the book up. Friction is still larger. No kinetic, so I have none of these types of energy here. Final state is checked. Third, I'll check work. Now, looking at this situation, I have transfer from two sources. First is the hand, and since displacement is to the right, the hand is providing a positive work, and friction is to the left, and friction is opposite of displacement, so friction is providing a negative work. So in other words, I have two of these, and I need to account for both of them. I made the negative one larger because it needs to account for both of these positive bars. So that means I have plus force hand on book delta D minus force friction on book delta D equals 0. So if the book is the only thing in the system, you have to be very careful of this because you have to literally recognize what is applying positive work energy to the system and what is applying negative work energy being removed from the system. Now, if I keep the table in the system, I will have kinetic energy, that's one. Final state, I have no kinetic, no gravitational, no elastic, but I do have some internal energy because the table's in my system and I do have a frictional force here. Now I do have some internal energy because the table's in my system and I do have a frictional force here. I also have some work done by the hand. So the hand is also adding energy to the system because again, force hand on book and displacement are in the same direction. So we have the initial kinetic energy plus force hand on book delta D, which is applying the positive work, equals force friction times delta D to account for internal. And since I'm giving force hand and the rest of this, I could very easily solve for force friction here. Now, I want to state again that mathematically these two things say the same thing, but if you are given other forces beside friction, I think adding the ground to the system makes your written equation a little neater. And if other forces are involved dealing with the work, then it is easily separated from the work done by friction. So what I'm about to put down here is not an official energy equation, but it is really the only way you will be using internal energy if you decide to keep the ground in the system.
Which I personally recommend you do.
And hopefully, as you noticed, the bar graphs help keep everything organized and literally create a mathematical relationship for you that makes whatever you are solving for very easy to find and isolate. In my next video, we'll be dealing with some true higher level energy problems that a bar graph is definitely a good idea to use in order to help you with. But for now, I'll end this here. Have a good day. This is Mr. M, signing off.